Hi, my name is Dinesh. I'm a first semester graduate student studying industrial engineering. My project is about design, analysis, and simulation of material handling system for a casting furnace. Let's proceed. I would like to start this presentation with a brief introduction about industrial automation. Most manufacturing process industries today have automated almost all of the manufacturing processes. In the scope of industrialization, automation is a step beyond mechanization. The main advantages of an automated manufacturing are higher consistency, higher quality, reduction of production time, simplification of production, reduction of manual handling, improving workflow, and the decrease of human injuries by minimizing human involvement. We are going to talk about Foundry because my project revolves around what Foundry is. Founding or casting, as it is commonly called, involves the pouring of molten metal into a mold that is to make an external shape of an article. The product that is formed is called a cast. The mold may contain a refractory course which determines the shape of the casting. It might have cavities. It might have a solid structure also. The work that we are going to do in this foundry is that we are going to try to minimize the human injuries that occur due to the manual handling of crucibles. Crucible is the container that is kept inside the furnace. This is the container which has the molten metal in it. We are going to do this by uh, making a semi-automatic robot that requires partial human involvement and reduces the risk of injury by a lot. How we are going to do this is what my problem description is. I'm going to split this presentation into three parts. First one is system configuration, second one is load capability, and thermal expansion. So when talking about system configuration, in any robot, the configuration of the robot is very dependent on the functionality of the robot. So we need to make a study to narrow down on what the perfect configuration, what links we require, what needs to be the joints, what should be the moving part, what should be the stationary parts. We need to determine the kinematics of the problem. So that is the system configuration. Second comes load capability. When any robot is manufactured, the payload of the robot is one of the most important specifications in it. It determines what tools and objects that the robot can carry at any point in time. Typically, the load of the robot is calculated when it is in the fully extended position. Payload can also be calculated as minimum braking load divided by the safety factor. Moving on to thermal expansion. Since you are working close to a very hot, very large source of heat, that is a furnace, we need to factor in thermal expansion of the robot. If thermal expansion is not factored in, there might be a huge error that might occur, or the robot might not even be functional. So this is one of the most important factors in this presentation. The coefficient of thermal expansion is what that we will be talking about. It is the constant that determines how much a material would either expand or contract during a temperature change. Metals like steel, copper have a positive coefficient, which means during the presence of heat they expand. Materials like carbon fiber have a negative coefficient and also less, which means they almost retain the same size when they are exposed to heat. Softwares and tools. uh, I'm going to talk about the softwares that I will be using in this project. First and foremost, I will be using SolidWorks to design and model the robot that we are going to use in the furnace. Uh, SolidWorks, I'm going to use it only as a CAD tool, uh, and I'm going to use this model in ANSYS to make to get the thermal and load analysis. ANSYS Workbench is generally a FEA, that is a finite element tool and an element analysis tool, which is usually used in the engineering field for simulation purposes. We need a CAD model to proceed with ANSYS. So the CAD model is designed on SolidWorks and is imported into the ANSYS Workbench software. The model is then meshed, and then the analysis is made. The third software that I will be using is called VREP. VREP is a configuration and model motion simulation software. This helps us to simulate the robot in a virtual environment to find out errors and issues that might arise during the development of the robot. Moving on, design and modeling. So my robot consists of 5 major components, starting with the base, the vertical pole, a main connector, an arm, and a gripper. As we see in this picture, we have the robot where this would be the base, this would be the pole, this is the main connector, this is the arm, the brown part is the arm, and then we have the gripper at the end. This is the fully extended position, and this is the lowest position of the robot. What this is that we will move on. In this pro project, we are considering two different materials. One is stainless steel, the 304 alloy, and the next one is carbon fiber. Stainless steel is generally used in high temperature applications such as like the furnace, so that oxidation does not occur. When steel is used in a high temperature area, oxidation occurs and rust forms. Hence, stainless steel is being used here. Also, stainless steel holds better strength when exposed to heat rather than other structural steels. One other option for us is carbon fiber. Carbon fiber is used in robotics applications widely because it has something called a negative coefficient of expansion, which means that carbon fiber contracts when it is exposed to heat. Even though it has a negative coefficient of expansion, the negative coefficient is very less and can be considered negligible. This means the expansion of the robot due to the heat that it might or might not be exposed to is considerably less than that of a metal. But carbon fiber is also considerably more expensive. So the results, even though might be vague, we need to factor in also cost and application when we go to the conclusion. Degrees of freedom. So like we discussed, we have 5 parts in this robot, and we are gonna make four. We need 4 degrees of freedom to do the required actions for the furnace. So we're gonna have 2 prismatic joints and 2 revolute joints. The pole of the robot will revolve or rotate along its own axis on top of the base. So a revolute joint is placed between the base and the arm. That will be the revolute joint. Then a linear or a prismatic joint is placed between the pole and the main connector. So this is a prismatic joint. We have a third joint which is also also a prismatic joint, which will be placed between the arm and the connector. So this helps the arm move within the connector front and back. We will have a fourth joint, which is a revolute joint, which will rotate the gripper at the end of the arm. Before we can proceed with the structural analysis, we need to find out how much heat will pass through the robot when it is exposed to the furnace. Hence, I have taken ANSYS and I have simulated at a temperature of 1000 degrees Celsius. I have taken the robot structure, placed and simulated it such that if the robot is placed close to a furnace, uh, which is burning at a temperature of 1000 degrees Celsius, this will be the heat flux in the robot. And this heat flux calculation will be carried forward onto the structural analysis uh, for calculating load. This robot has also been imported into VREP, and the joints have been made so that it can be simulated in VREP. By simulating it in VREP, what we are doing is that uh, we are finding out if there are any errors, if the robot can be functional, and such so. So once the robot is imported, we need to make a child non-threaded script and then add factors such as angular acceleration, angular velocity, and linear velocity, and then set target values so that we can use a robot. So first, I'm going to compare the results from carbon fiber. This is deformation, and this is stress. So here I am considering 2 kilos of load, which is generally the load that any furnace would have in a laboratory setup, and which is equal to 20 newtons. And I am also exposing it to the same heat flux that we have calculated there. So the maximum deformation found out in carbon fiber is 0.0023 meters, which is also 2.3 mm. The maximum 1 Meso stress is 93 megapascal. We are doing the same. In stainless steel 304 alloy. In this, we find out that the maximum deformation is 0.0052 meters, which is also 5.2 millimeters, and the maximum 1 Meso stress is found to be 93.6 megapascal. Conclusion: what we find out from this is that the deformation is twice as large in stainless steel robot than in the carbon fiber robot. Though it is twice as large, the maximum deformation is only 0.005 meters or 5 millimeters, which is a very low value considering the application. So carbon fiber can serve better in applications where high tolerance requirements are required. But in this situation, stainless steel alloy serves as a perfect choice for this robot. Thank you for listening to my project. That will all. Thank you.